I was checking if it is on the record. I will distribute printouts for any comments. And, when did you send it?
Yes.
Thank you. And maybe let me make some little announcements, not announcements, suggestions. If we track time for Aaron and check how long does it take to present, it would be helpful. Oh, it is the same problem between Mac and PC. So just in case, well, right now let's present whatever it is, but for final presentation you may get a screen capture of the whole slide and just paste it.
Well, it'll be on my laptop.
Yeah.
Huh?
You can convert it as a PDF?
Not the old thing, because he has some movies. You cannot embed movies into PDF. Also, since we have only 2 speakers, we are not in big rush. Let me invite Aaron to do a little exercise. So before going to formal practice, the overall talk, go to conclusion slide and pronounce it first. And then after you present conclusions, go to the beginning and start as you will normal. The idea for this suggestion comes from the fact that 15 minutes is really short time. There will be big famous people before and after Aaron, and I'm not sure that they will be generous enough to donate their time to Aaron. Could be otherwise. And there is from my own experience, there is a very big danger of getting stuck in the middle of the talk and not showing the most interesting part. So you're getting a little prepared, right?
Yeah, just
Okay, I'll make another announcement that may sound silly, but who knows. So, what are your main goals for attending the conference? Daniel knows the answer. You were talking to him, but
Just getting know the different dimensions of your research
okay.
and networking.
Uh-huh. Which is good. What is your main goal?
I guess I'm not really sure what my main goal would be off the top of my head. I guess I haven't explicitly thought about it.
You have a couple of minutes. You're not going, so you don't need to have a goal. You're a lucky man.
It won't be easier, Aaron, if you convert to PDF in your laptop and then send to Dimitri again?
I still have the issue of the movie though.
Oh,
Well, then we can present from
That was
your
the last. That was
from
the
your
last one I
laptop.
did.
oh yeah, they have a connection for iPad too.
Just
I guess
connect.
there was something
Connect.
we
I
can
have
remotely
I
connect
have
to
the
those
adapter with me.
Apple's things. I don't know the exact. You can connect Apple to the server remotely.
Yeah.
It will not. Well, we do not have anyone on the connection.
It's able to do in our
And
209.
if you do it
and it's
only
also
for the-
possible here.
Well,
You don't need to connect by the wire. You can connect it remotely.
Oh, through like Bluetooth or something.
you get substantial degrading quality.
Oh,
Yeah.
If you have wire, better use wire. There is also Apple TV where you can, and they get substantial degrading quality.
so is it connection through the Wi-Fi or Bluetooth, kind of like that?
They're both.
Wi-Fi kind of.
There could be. Okay, I'll stay entertaining. Fatima, what is your goal?
Let people know my research.
Okay. Ewan?
Advertisement.
Okay. You've heard the opinions. Now, star of today's show, Daniel Ramirez, what is your goal?
To get feedback from your paper, from your poster.
Right? So advertising, networking is super cool, but there is a practical, very important practical aspect. There will be like substantial amount of unbiased experts who will, if anyone approaches your poster, it means he or she is interested in your area and is expert in your area. You remember like some people at the group meetings were asking you questions. It will be sessions like this, maybe a little shorter, but you'll get some very inspiring questions. Sometimes you'll feel confused, but it is really big jump start for converting your posters into papers. And there is no doubt question that posters are made only in order to make papers. It's just intermediate step. So after you, people who will approach you, they will think that they interview you on your posters. But in fact, you are interviewing them on fresh ideas, thoughts, and feedbacks and ways to improve. Okay? And right after the poster session, instead of going to the pub or maybe simultaneously just take a piece of paper and write down anything you remember about questions and answers. And then you can switch off your mind and for another half a year, because when you write paper, like introduction is automatic. You just do copy paste. Well, not literal copy paste, but you collect ideas from literature. When you do methods, they're standard. When you do conclusions, it is what it is. When results, you just explain your figures. But discussion is most creative section. And there, you just copy paste your discussion with your peers at the poster. And then you have a protocol to get paper at a no time. But this is only the private opinion of several individuals. Do whatever pleases you, but just keep it in mind. Ready?
Low battery, and there's no.
What kind of plugin do you got?
Nothing here.
No, it's an outlet.
Oh, if you pull
Yeah.
this out,
I have no idea what
damage.
any of these are.
How long would it stay? How many?
It's at 4%.
Huh?
It's at 4%.
4%. We have very limited time to find.
Yeah,
You're gonna have to practice the speed run of your talk.
Maybe just have Ben go
Can you
first.
open any stuff
And you will charge
down the hall?
Yeah. It'll give enough time for it to.
Oh, here. Looks like an extension. Everything is occupied.
Yeah, I don't know which one links to which.
Just details the one platform there. They'll do it.
So after this long introduction, okay, let's charge your system and let's speak. I have email only from president of the university. Are you sure you sent it?
Would you know? Just like-
I sent it to the one that he emailed me from. I have it on a flash drive. If that
Okay, yeah, let's try it. Oh, yes, I see it. It just was delayed in transit. But if you, maybe, let's compete, maybe your flash drive will be quicker.
I don't.
It's go around the other side.
execute JavaScript.
Oh, yeah. So I guess a bit of preface. This is not going to be the longest presentation. Mainly because the research is very incomplete and I don't have that much done. But I'm going to present what I have at the moment. So I am currently looking at the effects of pacification on cadmium selenium dye.
Pacification? It's like Pacific or pacifist?
Pacification. So
Is it mine?
Passivation.
Is it-
Passivation, okay.
Yeah.
okay. Probably should have used that word instead. But
No, it's cute, but maybe not common.
so the main idea is that, well, currently what I'm working off of is I am looking at three different quantum dots essentially, and that are all the same, just have a different structure, and working from there and seeing how that changes it, and also how the passivation changes it. So this first category that we have is the PQE, which is the person that I got the systems from, and pretty much who I picked it up from. And then the second,
Punk.
Yeah, punk.
yes,
Okay.
yes. It's just this is like what he's referred to in like all the metadata and stuff. So the second one is bulk, which is I took the bulk of cadmium selenium and then attached the dye. And then the third one is VASP optimization, where I took the structures from a paper that Svetlana and company did a few years ago.
How much is
And
the difference from the first one and third one?
basically where I got them, essentially.
No, I mean, did you notice any difference or anything?
Like nothing too wild. I mean, if you look closely, you can notice some differences, but nothing exorbitant. And what I did is I passivated these in different ways and then optimized them. For example, here's some passivated systems. This is bulk AC passivated, which refers to the fact that it's passivated on the A layer and the C layer, and it's passivated with topo, which is trioctal.
Tetragonal? Or
No, trioctal
Directive
phosphine oxide.
Phosphinates.
Yes. Except they're modeled with just a methyl group instead of octal group. And so, and then here's the dye. The dye is a tribupyridine with an osmium core and a carboxyl group. That's what it's called.
How did you passivate this? I mean, how many topo groups and where it is?
So here, well, it's on the A and C layer, and the A layer, I believe, has 3, and then 6 on the C layer, and then I did this, and then I did a second category where I protonated. Specifically, I protonated a cadmium. No, that's a selenium. I protonated a selenium atom very close to the die, and so that's my optimizations. And then, so looking at energies, these are pulled directly from Gaussian, and so are in atomic units. So passivation, no passivation, we have, mid negative 3000s, and then it increases once you passivate them, which makes sense. There isn't that much difference, like half of an atomic unit between the non-protonated and protonated, but that's where similarities end, really. So I don't know how much I should. So
would you allow to interrupt?
yes,
So you're showing total energies.
yes, these
And
are total energies.
I may have overslept a couple of slides, but did you compute binding energies, or maybe inherited from anyone else?
No, I do not have binding energies.
But what is your opinion?
My opinion?
Not on the concept of binding energies, but on the binding of your carboxylic group to each, there is different chemical ways to bind. They both oxygen from carboxylic group may bind to one, let's say cadmium, or each of them can bind to different cadmium, or one can bind and another can be dangling in the air. Can you go back and just, even if you were not analyzing before, just tell
So-
your instinct about it.
Can't really get a good look, but here you can get a better look. So, I guess the intention was to get the oxygens to bind to two different cadmiums on the A layer. So,
And in fact, upon optimization,
it appears that it appears to have done as such. That being bind to two different cadmiums.
okay, two different cadmiums.
Yeah.
Okay. And what would be your expectation for binding energy, even if you never computed yourself and never looked on data of others? Would it be order of magnitude?
I really don't have a baseline for what's strong and what's weak.
And you can expect someone in the audience to give you little hints.
Yeah. I would imagine that it's more strong than weak.
Okay, but
How it would
what's
be.
a typical energy of binding? What were the data by Alyssa when she was?
I have not looked at any of the data.
But she was showing it on
Oh, she was
screen.
showing it.
Yes.
I don't.
I overslip slides very often myself, so it's fine. So should it be more or less than electron volt?
I'll take a gander and say more.
Okay. But you can be very relaxed and tell of the order of 1 electron volt. So the comparison to look at is to compute binding energy and compare with the thermal energy at room temperature, which is very small. It's like 2-3% of the electron volt, and anything above this value will approximately mean that it is stable, chemically stable binding.
Okay.
So do not, exact numbers and details are also important, but not as a first thing. You can just roughly tell, I do see numerical evidence that it is a stable binding. Okay. And please keep going, sir.
Okay. So total energies again. So next is DOS. I don't really know how accurate it is because it seems not that consistent. So I computed DOS for bulk and the VASP optimized ones. So for the AC pacified, protonated, and no passivation. So
Where is, oh,
No, that one is a similar question.
so what is 0, 1, question 2, where is Fermi energy? And question number 3, they all are like entangled. It's one big question. And which orbitals or which part of this electronic structure represent occupied orbitals and which are unoccupied?
So the 0 is right here, and I do believe that the 0 splits occupied and unoccupied. Yeah.
What is the line weight you use here?
This,
I remember like
I think this is like 0.025.
but I asked you to use the 0.1. That's why you got a very sharp peak.
Okay.
Point
Well, 0.1, like, it looked way too broad to me.
bright.
Broad.
Oh, broad. Okay.
So I
But-
tried a few
yeah.
different ones, and this one looked. Best.
So why you think that is not inconsistent? What are your expectations? What do you think?
Well, I expected the unpacified ones to not have a very large band gap, I guess, and the bulk one didn't have a very large band gap, but the VASP one had a band gap even larger than this one. And so, and I expected these to look a lot similar. I expected, you know, in the columns, them to look similar.
Did you able to take the fragmented dose?
Yeah, that's the next slide. So, I guess there's no reason not to. So, red is the quantum dot, blue is the dye, and T is the topo. So, green is the topo. And so, I got different results. So this is from -10 to 10. So it's kind of hard to see the band gap, but you can see it. But again, with the bulk, no pacified, there is no band gap. There's no gap at all. But
So the problem is seems like in the red line. In the bulk, no precipitation.
so the quantum dot.
Quantum dots, yeah. So maybe something wrong on the optimization. This quantum dots it didn't optimize correctly from the bulk.
And this, I guess since I don't have a conclusions page, so I guess I'll make a few observations. Because I don't have any formal conclusions because I'm far from done. But you know, just upon initial inspection, protonation of the quantum dot causes an increase in the band gap. You can see from here to here and from here to here the band gap is bigger, and it looks like the overall density of states is sensitive to the exact shape of the quantum dot, I guess. Because
I'm just wondering if you compare the DOS with these DOS. In this case,
it's not
all-
similar at all.
Yeah, so something is wrong.
Yeah.
Because they have no band gap, it's close band gap, or maybe they have no band gap, something in here. But in DOS, you saw they have a wide gap here.
Yeah. Well, there is a different axis compared to the PDOS and DOS, but I didn't notice that until it was a bit late to change it for today.
Question.
Yeah.
Or let's upload Ben for presentation. Go to discussion section. Any? Yes.
I have a question and a comment. I don't know if you ever talked about, but what does it mean to passivate something? I don't really know what that term
To
means.
passivate simply means to like here there's different, so there's the quantum dot, and each of the atoms on the quantum dot have different number of bonds, and essentially what we're doing is we are filling up the bonds of the cadmiums by attaching these topo molecules to them.
Is
So-
passivate is an action opposite to activate?
I suppose,
Yeah.
but makes it non-reactionary.
Okay.
Why would you want to make something not reactive?
Because this is a
It change-
quantum dot, it's a very small volume but high surface, so it's too reactive. It's not able to, it's need to stabilize, so that's why I need to passivate the surface.
Oh, okay. I didn't know that quantum dots were naturally reactive. Extremely.
Well, transition metals, do you see them often as isolated ions? Do you see any compounds where, well, not compounds, do you see transition metals like flying in the air?
Not really. Like inorganic materials are usually just in the middle as a core, right?
Yes, because the organic shell passivate them, because they, on their own they would react with something. And if you activate, if you have a metal organic complex and tear off one leg of this bug, there is a missing bond, you activate it, and then it can work as a catalyst. If you look what people do in Next Lab or Perceive Lab or engine, they have catalysis where this metal organic complex form temporary bonds and then activate some organic reactions. So transition metals, even if they are part of this quantum dot, they are active, and you do not want them to be active. The role of the quantum dot in this application is not chemical reaction, so you want to make them passive.
Alright. There you go.
Makes
That
sense?
helps. Yeah, that helps.
I have some. So, what is self-healing?
Self-healing,
Yes.
like in reference to this. Or
Yeah, absolutely. No. Otherwise, like, let me like put stitches on a wound.
No clue.
Let's go
Yeah,
to
nice.
your density of states.
Ah. Kind of. Oh.
Yeah.
Oh.
So bulk without passivation.
Bulk without passive.
Yes.
Yes.
Where is the gap? How big is the gap?
The gap is non-existent, pretty much.
Okay. Why? It relates to question by Daniel.
I guess because it's very reactive.
Yes. And what does it mean very reactive on the language of electronic structure?
I guess it means that there's a lot of electrons in the states near the HOMO and LUMO.
Yes, there are occupied and unoccupied states almost at any energy. So this compound can either donate or withdraw electron from any neighbor that will come. And if you guys can correct me, I can say something stupid because I never took chemistry, even freshman. But you know, there are like Lewis structures. It does something. When you
What kind of structures?
Lewis, yes.
Yeah, Lewis structure.
Lewis. Okay. Lewis structures.
Lewis, yes,
Okay.
when you like draw compound and then you draw like little ears of a bunny and like those are electron pairs, right?
We use dots, but
Dots, and sometimes you circle each pair of dots by. You had this, right?
yeah,
In your
Lewis structures.
okay. So there are if there is a active non-passivated transition metal on the surface, then it has some lone electron pairs that would participate into reaction if some stranger will come nearby. And on electronic structure and on the DOS, this lone pairs would correspond to populating gap area by occupied and unoccupied states.
Okay.
So this is a probably good catalyst, but it is not a good light emitter or substance to absorb light and give charge transfer. And can you point one figure down? Yes.
Yes.
What is the gap here?
The gap is almost 1 electron volt.
How come it is the same chemical composition?
I have no idea because
Any intuitive? Anyone?
Why gap is so?
Why gap opens upon optimization?
Because there's a quantum. They have no
Without any ligands.
because of confinement effect.
No. What I suspect that the bulk and optimized, it means not the presence or absence of confinement. I suspect, please correct me if I'm wrong, that you have the same number of atoms, same size of confinement, but in the bulk it means that symmetry of interatomic distance literally follows as it was in bulk, and vast optimized when the atoms rearrange.
I guess it's
So-
optimized in Gaussian, maybe, right?
so
Doesn't
yes.
matter.
Also,
Doesn't matter vast or Gaussian.
so yeah, the bulk is optimized, and so it goes out of the bulk structure. It's just it started as bulk as opposed to starting as the structure that I pulled from the paper.
So bulk is very symmetric. You probably have the structure.
I have
Up.
so
Next,
this is bulk.
one before.
This is before
Okay.
or
So,
optimization.
so the bulk,
This is before optimization.
yes, and it is what shows field gap, right? The gap with
No.
many active states.
No, I
No?
guess I didn't really label this well
Okay, interesting.
because I guess I would need to rename it when I present this further. But
Huh. So, what this middle picture? It is what you
it is
show.
what I optimized.
Okay, and the next one?
This is also what this is a different structure that I optimized.
Okay, so you optimize both,
Yeah.
and you report density of states after optimization.
Yes.
How long do you optimize? Do you
Until it finishes.
until it converges, or until it just runs out of compute hours?
Until Gaussian says that it's done.
Huh. Okay, then I can withdraw some of my comments.
So, like
It's maybe
here you can
because-
kind of see like what the bulk looks like. It does have a bit of symmetry, but it's not like bulk, like what it was originally. So
There was some confusion about the script, how he plot the DOS. So we just look on that, but we didn't figure it out yet. So
Okay.
that's maybe another issue of plotting this one, not only just calculation.
Okay, but generally it is a concept accepted in the community that if you compute electronic structure without optimization, then the gap will be filled. And upon optimization, the states will disappear, partially disappear from the gap area, because there will be formation structure, surface restructurization, surface reorganization. Fatima, is the right word? What people have in surface chemistry?
Surface reconstruction.
Okay, reconstruction. And upon this reconstruction, atoms on the surface bind to each other and erase these lone electron pairs. And this mechanism opens the gap. So some people call it self-healing, and your results seem very similar to this, even if they are not. More questions to Ben? If no, let's thank you once again. Do you believe you are charged enough?
Yeah, it should be fine.
And I have your slides on this one as well. We discovered that there is not enough charge.
You are the only participant in the conference.
Huh. It means someone was connected?
Maybe Brady.
Is he still in Los Alamos or he's on the road?
Yeah, good point.
Oh, it was me. Oh, I disconnected. So while you're setting up, I'll continue entertaining the audience. Did any of you registered for National Science Foundation? Oh, Daniel is a champion in other aspect as well. And so question is primarily to Vando. Did you register for NSF grant writing?
No.
It's your choice and your decision, but it is really, it could be beneficial. It's a course how to get money for nothing. So and by the end of the course, you submit true proposal, which will give you like 40K per year for the rest of your graduate school if you decide to go to.
That would be alright.
But it needs to register. If Daniel is interested, he knows what is the code for the course. Not from the top of the head, but you may see it. It's maybe like either English 400 or University 400 something. And
Well, yeah, you sent me an email about it a while back, so I could just find that.
Yep, and it's just 1 hour per week, so it shouldn't take all of your time. Does it work? 3 team input.
How long do you have to talk, Aaron? 15 minutes?
More like
Like, including
13,
questions?
12, 13.
Okay.
13 minutes?
Okay. I think it is yours. Yes, there was some motion.
put it in that.
It tries to update the resolution. Yeah. Maybe we should go from the PC. Would it be okay?
Let me just try one more.
Yeah.
thing.
Oh, maybe you're lucky. For 5 seconds.
Yeah, at this point, I don't know.
Come to post.
Fabric works, right?
Huh?
Fabric is okay? Material?
Yes. Well, now since Svetlana is paying for it, less her, but it is like not much more expensive.
Well, she's not here.
I understand.
Okay. That's all.
So I guess give a summary of my conclusions.
Yes, please, please. It will help.
You should do that when you actually give the talk.
I probably will.
Well, there is no negative advertisement. Anything that attracts attention works.
So I'm going to be talking about photophysics and specifically excited state dynamics and a lead halide perovskite nanocrystal. And this is just a quick summary of the results that we got. So the main observable in lead halide perovskites is photoluminescence quantum yield. And that is the main observable we attempt to try to compute and model with our simulations. And for that, you need to have your non-radiative and radiative recombination rates. And just for the heck of it, well, along the way, we would compute carrier cooling in the systems as well. We find that radiative and cooling agree pretty well with the experiment, while our non-radiative relaxation is a little bit quicker than what's seen experimentally. So with that,
It's kind of slow. Use the keyboard.
I think it's one more slide anyway. That's a nice video. So just a quick brief overview of how we designed our study. So we know we want to model nanocrystals. So the basic parameters, you can change their size, surface termination, and solvent effects. And for non-radiative relaxation in crystals, it's the ligands are important for that. So that's what we mostly focus on for our modeling. And since we're dealing with nanocrystals, it's basically we're limited to DFT or TDDFT anything, or higher level theory is pretty much just because it'll take too long for excited state dynamics. So we use DFT, and then it's known that there's strong spin orbit coupling in these perovskite crystals, so we have to use a non-collinear approach with spin orbit coupling, and then we use GGA functional, and we'll explain why we do that later. So here is the model that we built for a lead halide perovskite nanocrystal. So you can see in the middle, it's basically a 2 by 2 by 2 unit cell with a perovskite crystal structure. And this is about 99 atoms, so 27 lead, 54 bromine, and then 8 cesiums in the middle. And generally there's two ways that these nanocrystals are passivated. You can either have carboxylic acids and oleoamines passivated, or you can have oleoamine halides. In this case, we choose the carboxylic acid and the amines to coordinate to each of the surfaces, and then each atom is passivated, so you expect this is a fully passivated system. We should get near unity photoluminescence quantum yields in these systems. And so here is a plot of the density states what we compute. So we use spin orbit coupling basis with PVE functional, and in these systems, it's known that if you just use GGA functional with spin restricted, you get roughly correct band gaps. So for a system our size, which is about 1.5 nanometers, we get, if you just do spin restricted, you get about a 3 electron volt band gap, which follows from the effective mass approximation. But when you include spin orbit coupling, you get like a 0.7 EV reduce in your band gap. So, and that's what we see here. So at the end of the day, we get a qualitatively correct band gap for what you'd see in experiment for these systems around 2.4 EV, which is important for radiative and non-radiative calculations because it depends on the energy spacing or the band gap. And so it's generally known that the conduction band is composed of lead 6p orbitals, and the valence band is halide p orbitals hybridized with lead 6s. So, but the question is, what do the ligands do, or how do they contribute to the system? So this is a plot of the partial density states. The black curve is the full density states, which we saw previously, and red is the halide p contributions. Green is the 6s contributions. Pink is the ligand contribution, which is fully basically from the 2p orbitals of the oxygen. And in the valence band, we see basically little hybridization within this region. So here's just an image of the orbitals. You can see the hybridization of the oxygens with the lead and the bromines. And an interesting note is pretty much all the ligand, or all the hybridized states come from the oxygen. That we don't see any hybridization of the amines, which you kind of unexpected. And so that's the ground state electronic structure, and the main thing we want to compute is excited state dynamics. So to do that, we use our geometry optimized ground state structure as input for our excited state dynamics. So essentially what we do is we model the photo excitation, and then along a trajectory, we compute rates between interband, non-radiative rates between transitions. So in time, you get cooling to the band edge, and then on another time scale, you get the non-radiative relaxation across the band gap of the electron and hole. And to do this, we do a molecular dynamic trajectory to couple the electronic and nuclear degrees of freedom. And then at each time step, we compute non-adiabatic couplings on the fly using spin orbit basis, which is shown in the bottom here. And then we process those non-adiabatic couplings into state rates. And just to kind of give a brief overview of how this methodology works. So we just consider an orbital window from LUMO to LUMO plus 5. You have all the possible transitions, which you can label here. You can label those into like a matrix. So this would be like from LUMO plus 1 to LUMO, LUMO plus 2 to LUMO, so on and so forth. And then if you imagine this as each one of these squares is an amplitude and rotated it, these would give the probabilities of transitions, or the transition rates between the states. And that is basically what the next figure plots here. So this is called our Red Field Tensor. So this block up here computes interband transitions for the conduction band for electrons, and then these compute polar relaxin rates in the valence band. And so you can characterize each of these trends, which I'll just skip for brevity in this space. So once you compute your Red Field tensors, if you assume that the non-radiative relaxation occurs primarily across the gap from the HOMO-LUMO states. You can just use the matrix element corresponding to HOMO-LUMO as your non-radiative relaxation rate, and we get a rate of about 1 inverse nanoseconds, which is a little bit high compared to what's been inferred from experiments. So they infer that the non-radiative relaxation rates is about 2 to 3 orders of magnitude less than what we calculate, and I'll comment on that when we get back to the conclusions. And so those are our state-to-state rates, and then since we're doing a dynamics calculation, you need initial conditions. So this is what's being plotted here. So this is where we model photo excitation, which we compute from oscillator strings. One of the higher ones is from this state here to this state here, so HOMO minus 9 to LUMO plus 10, which is about a 3 eV transition, so it's something realistic. And then this figure here plots the dynamics in time for energy. So the x-axis is log time, so 0 is 1 picosecond, -3 is a femtosecond. Y-axis is energy, with 0 is the Fermi energy. So you can see the electron, we have initial photo excitation, and over time, the electron dissipates some of its energy to the lattice vibrations, and then it cools to the band edge. And the dotted line just represents average energy over the trajectory, and same for the hole. And for simplicity, we assume that these rates to single exponential fit, so we compute cooling rates to the band edge corresponding to about 4 to 8 inverse picoseconds, which agrees pretty well with experiment, where most experiments they see is around 300, or 3 inverse picoseconds, or 300 femtoseconds. So we approximate this as a single exponential, but you could suspect that in the conduction band for the electron, there's a strong spin-orbit coupling, so that's going to introduce big subgaps, and big subgaps, that's not going to follow a single exponential fit very well. So to look into that, we modeled this red dotted line is what our single exponential fit would be, and the solid line is what we actually compute for the dynamics. And for the spin orbit basis, you can see that up to about 100 picoseconds, there's a very quick decay in the valence band edge, but over time, due to this big subgap, about 2 eV between LUMO plus 1 and LUMO, there's a very much lower decay going on. And if you compare that to if you just did a spin-restricted calculation with no spin-orbit coupling, you see it's about 2 orders of magnitude quicker, just because we don't see that big subgap occurring here primarily. So take-home message is spin-orbit coupling is important if you're trying to model non-radiative or cooling rates for these systems. And so we can visualize these dynamics. So before we were just looking at energy relaxation, and here you can we spatially project the orbitals onto a 2D slice of our perovskite nanocrystal. So as time goes forward, you can see that there's slight changes in the orbitals occurring. So these blue lobes are the 6p, the yellow, or take that back, the yellow lobes are the 6p, and the blue lobes and spheres correspond to the bromine halide 6p. You can see the cooling rate for the whole to like the s orbitals, which would be in the center. And how much time do I have? 2 minutes. Oh, sorry, enough time. So that was non-radiative transitions in the conduction band, but you can also have possibility radiative transitions or interband transitions that can compete with the non-radiative, and we can compute those along the trajectories if you just compute oscillator strengths between all the bands. So if you compute oscillator strengths, you can get rates from the Einstein coefficients. And along trajectory, we don't see too much interesting. You see that there's a low energy heat interband transitions given off, and then after you relax to the band edge, you see bright PL coming from the system. And so to get our non-radiative rate to wrap up you get our photoluminescence quantum yield, you can assume that it's primarily from the HOMO-LUMO, and we compute that rate to be about 0.4 inverse nanoseconds, which is a little underestimated compared to theory and experiment for ultra cold experiments or in a vacuum or 0K measurement, that's what I'm trying to say. But it gives a pretty realistic result. And so if we plug everything into our photoluminescence quantum yield, we get 33%, which is right order of magnitude. That's usually what we try to take home at the end of the day as a computationalist for something this size. And you can see that this mostly comes from the non-radiative being kind of overestimated a little bit. And so to wrap up, the big thing that we see is 3 orders of magnitude larger non-radiative relaxation than expected. And one thing that this could be compared to is we only looked at one of the prominent surface passivations in these systems. If you consider the other one where it was the ammonium halide, it's generally, if you have a halide passivation, it's been seen in the literature that reduces non-radiative relaxation. So it could be that this surface passivation is ill-equipped for getting high luminescence yields out of these systems. And so with that, acknowledgements, fill-in cleaning group, people that give me resources and money, and it's the shameless plug for my poster that I'm also presenting this afternoon as well. So with that, I'll take questions.
Okay, let's thank Did he match in time?
Yeah, you were within like 10, 20 seconds, so.
Yeah.
Of the 15 minutes?
Of 12 minutes.
Oh. Okay.
12 and a half.
That's good, that's good.
Yeah.
Big speakers before and after will take your time, so it's good that you're ready. And better let audience to roast you with questions.
I put a time on each slide here, so you can take a look on which slide you spend how long.
That'll be helpful.
Any questions? Or suggestions for to make it better or worse? So, what are typical, you already told it, but what are typical quantum yields on experiment?
So,
I'm going to long one. And if they are off from your results, who is wrong and why?
that's what I was trying. Well, that's what I was trying to get at. With this part being overestimated, so typically with like freshly synthesized, these things emit around, you can get them up near 90% quantum yields, and then over time they may go down to like 50%. So what we calculated here would be considered like a bad emitter for perovskite standards. So, and that's mostly attributed to this non-radiative relaxation rate being too big, because if you just look at the equation, it's basically just one number divided by the sum of numbers. And this number is same order of magnitude as the radiative relaxation, so it's going to be around 50% for photoluminescence quantum yields anyway. So what I think is happening is that in experiment you could have 2 different surface passivations. If you just replace these guys with bromine coming out, and then there's been some reports in the literature of halide terminated surfaces having significantly lower photoluminescence or non-radiative recombination rates, or helping to promote slower non-radiative recombinations, which kind of makes sense because basically you're replacing this oxygen, which is a higher frequency vibration. But then if you put a halide there, it's bigger and slower, so it's not going to vibrate as much. So it gives less non-adiabatic coupling. So you expect that to lower the non-radiative rate across the gap by, I mean, if it did an order of magnitude, that would increase this number to like 70%, which is you would see in experiment.
Any other reasons?
I forgot the question.
Any other reasons for discrepancy? You mentioned the surface terminated by halides.
Yeah, and there's also GGA functional, which is, it kind of underestimates, or it overestimates gaps between states a little bit. So someone published a paper on that a while ago, and I think the take-home message was it's like 2 to 4 times slower. So it would improve our rates a little bit if we use like a hybrid functional. But then again, that's going to change our gap too.
Someone, you mean Akimov?
Yakima, yeah. He'll probably be there, so I should probably
He will.
say his name. But so that's another issue. Then there's also
What is the typical size of experimental perovskite dots?
they're usually like 10 nanometers, 10 to 8, and ours is probably 5. So it's mostly surface. So basically, all we're measuring is surface effects, or majority surface effects, instead of the little bit of bulk material that's on the inside compared to outside.
So could it be enhanced surface effects in your results that are responsible for discrepancy from experiment?
I mean,
Because of the size is basically by order of magnitude or half of order of magnitude. You are doing 1 nanometer and experiment is like 5 to 10.
yeah, but I would expect that to impact the cooling rates more than the non-radiative, just because. Yeah, you'd have to scale those the same.
Mm-hmm.
So if you assume that if we made a bigger model, it would decrease the rate across the gap, that would slow down our cooling rates too. So
It may also increase the density of the state and then increase the
Yeah,
coupling
that's
between the
true.
state.
yeah, that's true too.
So you may want to create a backup slides with listing all sources of discrepancy. If no one asks, you do not need to show your weak spots. But
Then Rashba effect, just because, well, if you get the chance to say Rashba effect, you just should, because people,
blame Rashba for everything.
yeah.
That is my question too. What is Rashba effect? I've never heard of it.
So it's the coupling of like electronic spin to your crystal structure.
What kind of spin? Sorry.
So like electron spin,
Oh,
so
electron.
up or down spin, it couples to the crystal lattice, like any sort of fields produced in there. And then the take-home message is it usually slows down non-radiative the combination because you need a little bit more energy to recombine.
Thank you for that.
You were about to ask something. Sorry for cutting.
Was I?
Or maybe you were scratching like.
Oh, yeah, I was probably just doing that.
Okay.
Can you go to the slide where you show the Red Field Tensor? Probably I just didn't pay attention. So why you show the table? Right corner. Yeah.
To give people a better idea of, maybe it doesn't help, I don't know. But maybe, like, it's hard to visualize what each of these blocks mean. So if you project it like along one of the axes, it's like this would be your HOMO -1 to HOMO transition.
Oh, okay.
HOMO -2. So it's just a one-dimensional or 2D plot to simplify things instead of a 3D.
Okay, well, I guess maybe you need to explicitly state that. Otherwise, it doesn't make sense.
So it's like zoom in into this bigger figure.
Projected Red Field Tensor.
But projected Red Field Tensor is very specific terminology. Maybe specific up to one person in the world.
I kind of hope these white lines kind of helped, or people would connect dots at this big bar. Is this one, these smaller ones, or this one? But yeah, maybe I'll just take it out to, or I could just leave it in and it'll provoke questions.
Or you can like finger it with either your pointer or with actual finger and tell like if you zoom into this white area, maybe you told it, but
I think I just skipped it just because I was pressing for time.
It might help if you flip the order, because like if you kind of imagine, you know, projecting that on there, it seems like that's kind of the opposite direction of how it would go, right? If you were to just kind of like slide that up there, because you're looking at the other face of it from the way that you're projecting it.
Yeah. I don't know. That's work though.
It's true.
I also have a question about the slide you show the single exponential fit. So what's the point of this slide?
To show, well, it's kind of cut off here just because of the issue we've been having earlier. But you see, they both show like similar decay within like up to -1 100 scale, but not even -1. But they show similar decay like with like around -2, and then once it gets closer to the band gap, there's an extended decay tail. So I'm just showing that compared between spin orbitals that we use and spin restricted, you're gonna get like a 2-order of magnitude difference just based on the energy differences in the density of states.
I'm not sure if this kind of comparison makes sense. So the initial condition is different, right?
I tried to make them like this is the biggest transition I had for the spin restricted, so it's 0.3 eV. This one's like 0.4 eV. But I guess that still doesn't change the fact that you still see this really long decay.
Can you say that the this fit and time dependence will not change substantially if you excite a couple of states higher or a couple of states lower?
Right.
But how about the orbital? Like, in addition to initial conditions, how about the intermediate states? So the charge density distribution is also the same for spin polarized and SOC.
I guess that I can't comment on, but what I can tell you is non-radiative rates, they're inversely proportional to like the energy difference. So if you have a big energy difference, you're gonna have a slower rate. So, and that's kind of what this is showing here. Whereas, like this is probably, I don't know, within room temperature spacing between these energy states. So you see much quicker decay to the band edge.
The question, did I answer the question you asked? Or? Yes.
I guess it's also important too in another sense, because experimentally, and I think it was crystal like thin films, they saw, or they observed like emission above the band gap for, it wasn't for bromide systems, but for iodine. So if you were trying to model that, like emission above the gap, like this is really important because you have to have a longer lifetime in like your LUMO +3, LUMO +2 states.
So what's your conclusion from this slide?
So the take-home message is to model carrier cooling in these systems, you have to have spin orbit coupling. Otherwise you get way too quick rates.
So basically you're telling, look at me, I can do spin orbit.
Pretty much, yeah. That's why I showed the first slide too, showing that that's, I guess I didn't mention it, but we compute excited state dynamics with spin orbit coupling, and not a lot of people can do that, or haven't done it yet anyway.
And this is not small perturbation to overall answer. You see major consequences of taking into account spin orbit.
Yeah, almost 2 orders of magnitude. Like this tail extends out to like 0.5 out here on the time scale, so it's basically 2 orders.
Questions? More questions? One? Any comments, any suggestions on the style of slides? Like if you're not comfortable with size of fonts, or
I try not to pack too much into it, but
Who are you presenting these to mainly?
people smarter than me.
People smarter? Oh, okay. I just want to know what the crowd was like, if they were just a group of engineers.
Professionals. The person who discovered these. He's
Oh.
talking right before me.
well, I have a simple question. It doesn't affect any science. Why do you put titles on the bottom rather than on the top?
I don't know. I just liked it like that.
Okay. Is everyone fine with this?
This is okay because it's kind of not a main title. It's kind of slide title. If anybody want to do
Yeah, like my main titles I put on top.
Yeah.
And now you don't have to strain your neck as much too looking down.
Okay. So you can start like, I care about your necks.
Oh, you old people.
Anything? Any slides to remove, or maybe something is missing? Any slides to add? If Aaron will be first and the only speaker about perovskites, maybe one could add like 3 slides of introduction what they are, but
Right.
there will be speakers before him, so it's probably justified to be so technical.
When is your talk?
Tuesday after lunch.
Okay.
Can you write it down in the title? No, it is Tuesday after lunch. Welcome to my talk. Just in case if a stranger came and told you. Well, I don't care, but many people, I don't know it's right or wrong, but many people, maybe for, it is a notice to retarded ones. On the first slide, they tell which conference it is, which talk it is, and even what time is it.
It is pretty common, I guess. Yeah. I saw in many, but time is like in automatic in PowerPoint. So they updated time.
No, time not like what time is literally, but like scheduled time for beginning of the talk. Or maybe like you at the last slide you put the code of your poster, but you may put code of your talk at the beginning, because if maybe someone wanted to go to different session. And or specifically to this session and watch for your talk and look at, I wanted to look for this talk. Oh no, I do not want. I better leave.
Yeah, I could fit that in my green box.
Good.
You can work on acknowledgement slide. I mean, in acknowledgement slide, you can put some picture like your group picture or NDC picture.
I don't think we have a group picture.
You can make one, but it's not primary thing. Did you?
It's acknowledgement. The
Have you
last
seen
slide, yeah.
talks by Dr. Hobby? No.
On the, yeah.
You did?
On the, I forgot which conference.
Tell regional.
Oh no, not that.
We should make him
As a
to
conference here.
present departmental seminar. He starts telling what North Dakota is, how it is connected to Game of Thrones, and winter is coming. Well, you don't need to do it. It's just
He's after me, so he can.
okay.
He's stealing his material.
Like Dr. Kilimov's talk in the Sunnyvale. Dr. Kilimov talk.
But he puts
He showed the
different things on-
ancient figure, and then with the quantum dots things, how the cluster breathing, everything.
Can we go to slide number 7? Yes. Do you think this slide is necessary?
Maybe not absolutely necessary. I just put it in there to explain what the Red Field Tensor is. Because it seems like nobody, it's like, people probably haven't looked at it before. And if they knew that basically this represents state-to-state transitions, if you laid it out like this, from here to here, then to here, they might get it.
Maybe in a short time, no one will be able to follow this slide, but if someone wants to perceive everything, it's probably useful. Okay. Enough?
In slide 6, previous one. So, what is the EO meaning? Is exciton is relaxing through the state, or is just a particle, electron and hole?
Just electron hole relaxes the band gap. Well, this is probably a little bit of propaganda. because we
Yeah.
compute them.
I'm just
independently.
wondering why you put the both in the electron and hole both in the same place. It's kind of, it's like, it look like they are moving together as excited and they're relaxing to the, still they are excited, it's kind of like that.
So physically it kind of correct, but literally it is deceptive because there is no bound exciton in this work.
Right. Like I said, it's kind of propaganda, but I guess
Would it be easy if instead of electron and hole, if you put just hole or just electron, then in, and it's
Well,
relaxing to the
he
same.
knows how to answer if someone picks him. No, it's only propaganda. Actual results are much simpler. And if, well, I agree that I probably would do a separate electron going down, hole going up, but then Aaron would need to change his first and last slides because he's
No, I
using
mean,
his own pictographical language of this blue and orange circles.
so I guess you don't need the both electron and hole. You can show just one as an example. This is just as an example, maybe, right? Yeah, how is relaxing.
Do you think it is critical to change it or optional?
I guess it's optional because it's like it's not your research slide, so maybe you have
Still, it's a little bit misleading.
It is.
Yeah.
It is misleading.
I guess the big thing I tried to show is this way it's time. So you get cooling at one time, and then a little bit, then later you get non-radiative relaxation.
And also,
You can't do that with
yeah.
the band picture.
But this is not the care cooling, right?
Yeah,
I
it is.
mean, no, I
Well,
mean
this
this
part is.
this what's it called? What's it called? Is Carly bracket? Yeah.
What?
What is this Carly bracket? You meaning this one to this one is a
It's time interval for cooling.
time.
But the,
So this is like one, like some relaxation,
Mhm.
some more energy dissipation. So you're kind of supposed to think of this as like
This is a time, right?
yes, we are assumed to be mind readers and understand that it is a timeline. It is not labeled, but
Okay.
maybe explicitly writing that it is a time would be a help.
Or maybe cooling because isn't it rate instead of K?
yeah, but you can get your rate from the time interval. I guess. So it's maybe I should explain just this figure more. I'm going through.
And also, I'm not, maybe I don't understand this way either. So in the first photon, I mean, in the blue curve, so you're showing this absorption process, right? And then it's relaxing to that ground state.
Our EG is gap, energy
EG is
gap. Mhm.
Then why you put the photon H mu? The energy I mean, yeah, blue H.
Because we model a photo-excited relaxation. So this is like our initial condition.
Okay, so this is the ground state, right? EG.
Are we excited?
It is a frontal orbital or ground state?
Okay, so your
So
point is
exciting
time
above
point
the
should
gap.
be below.
Right.
EG.
So this arrow should
Yeah.
be down more, I guess.
Yeah, then H mu should be larger than this one, right? This is not H mu.
Right. Maybe I'll just say this is gap and
Yeah, so the EG is a frontal orbital, maybe, right?
yeah, LUMO, homo,
Lomo and homo. Yeah.
energy difference between
Yeah.
them.
So H mu is not. It's not H mu here. Maybe.
Yeah, technically we picked it all apart.
Mhm.
I guess.
So I guess it would be better if you add another line below the EG. Is exciting from that line, and then electron is relaxed to the EG.
Yeah.
Is it would be better? I mean,
I would have to rearrange all this stuff.
Electron is excited from the
I guess you can do that because they have a space to add another line. I guess it would be fine. Yeah.
so electron is excited from the valence band, conduction band, right? So I think it's
Would
better
you
to
be happy
put
with
it on.
if you look at something like this?
For Yeah, that's mhm.
Like electron and hole
That's what I'm saying. Yeah.
separately, and then we're combining it there.
So it is exciting from the balance band and relax to the low mode with low mode band.
Right. Yeah.
Well, if time allows, if you have nothing to do on a plane, or if talks before you will be boring.
If you think that you don't have a space in the slide, so you can just add one line. You don't need to show the whole. Just show the electrons. Scan to the EG.
Now I'm just trying to remember how many times I show this thing. Maybe just it's I guess only once. So yeah, it wouldn't be too much work to. But that'd be the only slide I'd have to change.
More questions? Then let's thank Aaron once again. Let him collect comments, written comments for improvements, and have a safe travel.
I have a quick question on the slide 4 actually. It's not a question, I'm just wanting to know a clarification. Is it 4? Yeah, slide 4.
Or use it onto this one.
Yeah. So what is the E for me? Is that
For the
because
energy.
E for me is not any is related to the frontier orbital, right? Is that you mean or
So
So-
Fermi energy is positive here.
I think so.
This is fine, but I wouldn't advertise it widely.
Right.
Most likely it is not wrong, but it is not typical.
It was just the energy or the value that I had to shift it from the.
Yes, but
So absolute value of that, plus or minus.
Absolute
I don't remember.
so you can keep it on extra slide or on a side if someone asks.
I just
Positive Fermi energy is not something to, even if it is correct, if it is not something to brag about. It would be.
It would have. I'm trying to remember. Well,
If it would be minus 1.73, then you can keep it. But
I guess it's not necessary to read the Fermi. Is it related to Fermi? Any discussion in this slide? This energy Fermi information?
the label.
It's just labeling, I guess.
Oh, I mean like the x-axis label.
As a gap is important, but this for me is not important in this discussion, right?
yes,
You can do that one.
yes, correct. What is 238 in nanometers?
Like 5, 10.
1240 divided by 2.38.
Yeah. Well, you may. It's not necessarily
Is that
necessary to show it, but you can verbally tell it.
Mm-hmm.
For those who are from experimental background,
Yeah, because
specifically for Maxim. Okay, so we are done.
looks like it.
Oh, yeah. Have a safe trip, using conference.